Section 10.1, Radical Expressions. So as the semester winds down, we finally take a look at Chapter 10. You should have memorized at this point your perfect squares through 20, your perfect cubes through 10, the first 5 perfect fourth powers, and the first 4 perfect fifth powers from your handout. We begin the section with a definition. We talk about the square root of a number. Brown box at the beginning of the section. It says a number b is a square root of a if b squared equals a. If b times itself is a, then b is the square root of a. So, let's talk about the square root of, say, 25. What is the square root of 25? The square root of 25 is going to be a number that when squared gives me 25. What number squared gives me 25? Well, 5 squared gives me 25. But there is another. There is another number that when you square it, it also gives you 25. Do you know what number that is? What other number when squared gives me positive 25? If you square negative 5, you also get positive 25. So a problem like this may say, find the square roots. Find the square roots of 121. Find the square roots of 121. And when the question is asked like this, we're looking for both square roots, not just the 11, but also the negative 11. And you are welcome here once again to use the notation plus or minus 11. That's a way of writing both numbers at the same time. Now, when I use a square root symbol, square root of 25, we're talking only about the positive answer, which is also called the principal square root, the positive square root. So if I use a notation like this, I'm only looking for the positive 5. And if I want to ask you what is the other square root of 25, I'll say it like this. Evaluate negative the square root of 25. That negative is just floating, and the square root of 25 is 5. We have a brown box at the top of 651. Here on the second page of our section, it says square root of a is the positive or principal square root of a. Negative square root of a is the negative square root of a. Now, as we ponder on these square roots, let's think for a minute about this. What is the square root of negative 25? What times itself would give me negative 25? Well, it's not 5. 5 times itself is positive 25. It's not negative 5. Negative 5 times itself is also positive 25. What number times itself will give me negative 25? Well, a number times itself is either going to be a positive times a positive, which is positive, or a negative times a negative, which is also positive, or it could be 0 times 0, which is 0. There is no real number that will give me, when squared, a negative result. So if you take the square root of a negative number, the best we can say right now is that that is not real. And for the purpose of taking notes, I might write not real. That's just for note taking. The little tilde out front means not real. On multiple choice, on any quiz or test, I'll write it out. Let's go ahead and turn to the homework and get some of these out of the way. Our homework beginning here on page 658. And let me warn you, in this section, it is imperative that you pay close attention to the instructions. Pay close attention to those instructions. That will save you a lot of grief. Number 14. The instructions say, find all square roots of each number. So find, in number 14, the square roots of 100. Well, we know that real numbers have 2 square roots, except for 0. The square roots of 0 are, well, there's just the one, just 0. But for any positive real number, it's going to have 2 square roots. 100 is a perfect square. You know what squared gives me 100. 10 and negative 10. Or again, use your plus minus notation. Now starting with number 24, the instructions say find each square root. I would more likely say evaluate, because the square root sign is an operative symbol, and when you see it, you know what to do. Evaluate number 24, square root of 81. Evaluate the square root of 81. Well, square root of 81 is 9. Why? Because 9 squared is what gives you 81. The square root is like unsquaring. We're unsquaring that 81 and asking the question, what squared gives me 81? Number 30, evaluate, I would say. Negative the square root of 196. That negative is just sitting out front floating. So it just follows the rest of the problem along. And the square root of 196, another memorized perfect square. You know that 196 is the square of 14. If it helps to have your handout by you while we work these problems, that's fine. It is preferable that when working the homework, and certainly on a quiz or a test, that you not have your handout with you. Those should be memorized facts. Number 32, negative the square root of 49/36. The negative's floating. Now, what do I multiply times itself to get 49 over 36? Well, when you multiply fractions, you multiply the tops. So what could you have in the top times itself that would give you 49? 7 times 7. And in the bottom, 6 times 6 would give you that 36. In other words, when you take the square root of a fraction, you can actually take the square root of the top and the square root of the bottom. And that is a rule that we will formalize later on. You can check this. The negative is floating. What is 7/6 times itself? 7/6 times itself. Multiply the tops, multiply the bottoms. That works. Number 34. We have a decimal. Evaluate the square root of 0.16. Well, I need something times itself that's going to result in a 16 with 2 decimal places. When I'm multiplying, I count all the decimal places in the problem. What number times itself gives me 16? A 4. What number times itself gives me a 16 with 2 decimal places? A 4 with 1 decimal place. Now, does that make sense? Let's check it. 0.4 times 0.4. 4 times 4 is 16. We count the decimal places in the problem. 1, 2, and give that to the answer. 1, 2. Yep, that works. While we're thinking about it, what if I ask you, what is the square root of 0.0169? The nice thing is we have an even number of decimal places. If that were odd, this would be quite a different problem. We need our answer to end up with 4 decimal places when we check. When we have our answer and we multiply it times itself, we need that result, that check answer, to have 4 decimal places. So my answer to this square root is going to have 2 decimal places. What times itself gives me 169? 13. A 13 with 2 decimal places will give me back a 169 with 4 decimal places when I check. 13 times 13 is 169. I'm not going to go through the long multiplication. We know 13 times 13. And there are 1, 2, 3, 4 decimal places in the problem, so we give the answer 1, 2, 3, 4 decimal places. And so that checks. Number 36. Number 36 asks me to evaluate the square root of negative 64. Well, we've already figured out you can't take the square root of a negative, not with real numbers. Now next semester, college algebra, algebra with apps, we will introduce a way of answering this. But for now, we're sticking with just real numbers. The answer to this is actually an imaginary number, but we're not going to worry about it right now. Best we can say is that this is not real. Look at number 38. Negative the square root of negative 100. What I want you to understand in looking at this problem is that these two negatives cannot see each other. The one out front is floating, and the one inside is having its square root taken. And until that square root sign is out of the way, the inside and outside parts cannot see each other. So the first thing I would have to do is let that negative in front float, and now take the square root of negative 100. Well, you can't do that. That's not real. The thing in this problem I want you to understand is those two negatives do not make a positive and give you an answer of square root of 100 is 10. No. Those two negatives cannot see each other, so we're actually taking the square root of negative 100, and right there we can stop and say this result is not real. All right, number 40. Square root 59. Now, what did I say earlier? In this section, you had better pay attention to instructions. The instructions here say find the square of each radical expression. Find the square. Well, let's take a minute over to the side here and let's work a problem that contains a perfect square. 59 is not a perfect square. Find the square of, let's say, the square root of 9. Well, that means take the square root of 9 and square it. Well, the square root of 9 is 3, and you square that 3, and you get your 9 back. And that's going to happen every time. A square and a square root undo each other. A square root is undoing a square. It's unsquaring. So the square of a square root basically puts you back where you start. Now we'll have more words about that here at the end of the section. It's not exactly that clean of a process. But I want you to think about this. This is some number. The square root of 59 is some crazy, irrational number. In fact, it's going to be 7 point something. Because what? Square root of 49 is 7. Square root of 64 is 8. So this has got to be between 7 and 8. It's going to be 7 point something. But the instructions said what? Find the square of this square root. Well, I really don't care what the square root of 59 is. What I know is that if I square the square root of 59, I'm just back where I started. Don't make those tougher than they need to be. I don't need to go through this process each time. I did it with a 9 because that's a nice perfect square and we can see what happens. The square root drops it to a 3 and then you square it right back to a 9. So anytime you are looking for the square of a square root, it's just going to be that thing inside. So long as the square root itself is real. If that were a negative 59, we'd have a whole different situation, and we're not going to worry about that right now. Pay attention to the instructions. In problems 39 to 46, you're being asked to find the square of each square root, which basically just dumps back out that radicand. Let's talk about some terminology before we go on. The symbol that we use is called the radical sign. The number inside the radical is called the radicand. So if I simply ask you, what is the radicand in this expression? The radicand is 64. So there's some terminology that we need to know. We'll come back to this little figure, and I have one more bit of terminology to give to you, but we're not quite ready for that yet. Let's continue in this homework set. Now looking at the problems starting with number 47, and I'm going to grab a handful of these. Let's read the instructions. Determine whether each number is rational, irrational, or not real. If a number is rational, give its exact value. If a number is irrational, give a decimal approximation to the nearest 10,000th. Use a calculator as necessary. You are welcome to grab a calculator to get those decimal approximations. I will not ask you for that on a quiz or a test. I will not ask you for a decimal approximation with which you'd have to use a calculator. Here in the homework, it's not a bad idea to practice that. Now it says determine whether each number is rational. You remember we used these symbols back in chapter 1. Rational, irrational, or not real. If it's rational, give its exact value. If it's irrational, grab a calculator. If it's not real, we're done. That's all we can say. Well, an example of one that's rational would be our square root of 25, because his answer is 5. 5 is a rational number. An example of an irrational, square root of 2. Square root of 2 is approximately, if you grab the calculator, 1.414, but it's irrational. It goes on forever. Never repeating, never terminating. An irrational number. Chapter 1. And of course, a not real example would be one in which we're taking the square root of a negative number. That would be not real, and we'd be done with it. It turns out, and your book discusses this, your book talks about this on page 652. If we're taking the square root of a perfect square, those are those numbers on your handout. You've memorized the first 20. It also includes, you remember our 49 over 36? That's considered a perfect square. It's a fraction, but it is the perfect square of what? 7/6, which is rational. If you're taking the square root of a perfect square, the answer will be rational. If you are taking the square root of a non-perfect square, the answer will be irrational. And if you take the square root of a negative, the result is not real. By the way, rational also includes that square root of 0.16. 0.16 is a perfect square as a decimal. That would also be a rational answer. It's a terminating decimal, and we know that that makes it rational. So, let's grab a few here in this homework from 47 to 58. Let's identify if they are rational, irrational, or not real. If they are rational, we'll give the exact answer. If they turn out to be irrational, we can grab the calculator and do a decimal approximation, although I'm not too worried about that. And if it turns out to be not real, well, then that's the end of that. So I've grabbed number 48, number 50, number 52, and number 56. Let's determine whether each of these is rational, irrational, or not real, and then give an appropriate answer depending on what we determine. Square root of 169. Is 169 a perfect square? Yes, it is. So we know that our answer here will be rational. This is how I'd write it in multiple choice. I'm not going to use the Q, the I, and the not R. This is how I'd write it on a quiz or a test. If you want to use the capital double-barred Q here in your notes, you're welcome to. Well, if it's rational, we should be able to give an exact answer. We know that the square root of 169 is 13. Number 50. The square root of 33. Is it rational, irrational, or not real? Is 33 a perfect square? No, it's not. It's not on our list of perfect squares on our handout, is it? It's between the perfect squares 25 and 36. So 33 is not a perfect square. So this represents an irrational number. And the instructions said, and I'm saying if you want to, because I'm not going to have you do it on a quiz or a test, but if you want to, grab a calculator and approximate this to the nearest thousandth, that is 3 decimal places. And I'm not going to grab a calculator, I'm going to grab the margin of my text, where she has the answer approximately 5.745. And I write that just in case you want to verify with your calculator that that is correct and that you know how to use your calculator. For our next one, is it rational, irrational, or not real? This negative out front is just floating. So to answer the question, rational, irrational, not real, we're just going to look at the radical itself. And that radicand, is that radicand a perfect square? Is 81 a perfect square? Yes, it is. It's the square of 9. So the result of this expression will be a rational number. And in fact, we know that it's going to be, that negative's floating, it's going to be negative. The square root of 81 is 9. And finally, number 56 wants to know about the square root of negative 47. Well, you can't take the square root of a negative in real numbers. So all we can say here is that this is not real, and we're done with that one. Let's look at number 60. Number 60. Again, paying close attention to these instructions. It says, without using a calculator, determine between which two consecutive integers each square root lies. Now, I've kind of mentioned this a couple of times already in passing, didn't make a big deal of it. 43 is not a perfect square. 43 has a square root that's irrational. And what she wants to know is, between what two integers is the square root of 43? If I were to punch this up on a calculator, would it be between 2 and 3? In other words, would it be 2 point something? Would it be between 10 and 11? In other words, 10 point something? What perfect squares do we know to either side? Just below 43 is the perfect square 36. And just above 43 is the perfect square 49. Those are the two perfect squares on either side. What are their square roots? Square root of 36 is 6. Square root of 49 is 7. So the square root of 43 must be between between 6 and 7. That's all she's asking. Now, if you want to grab a calculator and verify that it is 6 point something, some crazy irrational number, but 6 point something, something between 6 and 7, go ahead. But for that little set of problems, that's all we want to know. Square root of 43 is between what two integers? All right. Square roots are great, but that's not the end of the discussion. Square roots undo a square. The square root of 9 is 3 because 3 squared is 9. But we can also deal with cubes. 5 cubed. You know that, you've got that memorized. 5 cubed is 125. How can I write this in radical form? Well, what I do is I write a cube root. Cube root of 125 is 5. The cube root undoes a cube. And I put a little 3 right here in the check mark. Something to the 4th power. 2 to the 4th is 16, which means that the 4th root of 16 is 2. So we have these higher roots. And let's go back to where we had labeled a couple of terms. We had our radical sign. Inside we had the radicand. And now, let's talk about what we call this number in the check mark. That number in the check mark is called the index. It is called the index of the radical. When I'm talking about a square root, I understand that the index is 2. I understand that the index is 2, but I don't write it. It's just like when I write 1x, but I don't write the 1. 1x is just x. Or y to the first power. We don't write that 1. Well, in a square root, we don't write the 2. In any other root, we do explicitly write that index. But in a square root, we understand that the index is 2. All right, so let's do some of these higher indexed radicals. Let's jump down to number 74. Number 74, in my instructions, she says find each root. Once again, I will say evaluate, because that radical sign is an operative symbol. And so it tells you what to do. You're finding a root. Evaluate the cube root of 343. You've got your perfect cubes memorized, and so you recognize 343 is the cube of 7. Cube root of negative 125. Let's spend a moment thinking about this. This asks the question, what number when cubed gives me negative 125? What number times itself 3 times gives me negative 125? Is that even possible? Yes, it is. It is because this is an odd index. And an odd number of factors will retain the sign of the factors. In other words, think about this. What is negative 5 times negative 5 times negative 5? Every pair of negatives makes a positive, but now I've got what? 1 left over. When I multiply, an odd number of negatives is negative. So with an odd index, you can take the radical of a negative. And so here it will be negative 5 because negative 5 cubed is negative 125. And that works because the index is odd. For an even index radical of a negative is not real. Even index of a negative is not real. Odd index of a negative presents me no problem. My answer will simply be negative, as we can see here in this check. Number 82, negative the 4th root of 256. You've got your 4th powers memorized by now, hopefully. If not, keep working on that. And we recognize that 256 is the perfect 4th power of 4. The negative out front floats, and the 4th root of 256 is 4. Number 84. The 4th root of negative 256. And what did we say? If we have an even index of a negative, that's going to be not real. You cannot take an even index root of a negative number in real numbers. Like I said, next semester we'll come up with a way to handle this in what's called imaginary numbers, and we'll explore the world of complex numbers. But for now, we're sticking with real numbers, so the best we can say, the even indexed root of a negative is not real. Number 92. The 4th root of 81/16. Like we discovered with square roots, you can take the square root of the top, square root of the bottom. Well, that works here. We can take the 4th root of the top and 4th root of the bottom. 4th root of 81 is 3. Fourth root of 16 is 2. And if you don't have your fourth powers and fifth powers memorized at this point, this is going to be a choke point for you. You need to be able to spot those perfect fourths, perfect fifths, as we go through these problems. This one's easily checked. What is 3 halves to the fourth power? It better give me back the 81 sixteenths. Well, we know that we can distribute that power, section 4.2, giving me 3 to the fourth over 2 to the fourth. 3 to the fourth is 81, 2 to the fourth is 16. So that works. Number 94, negative the fifth root of 1/32. That negative is just floating, so he hops right into the next step. And now we take the fifth root of this fraction by taking the fifth root of the top. Fifth root of 1 is 1. Any root of 1 is 1. Square root of 1 is 1. Cube root of 1 is 1. And here the fifth root of 1 is 1. And the fifth root of 32, you should recognize 32 is the perfect fifth power of 2. That 2 to the fifth is 32. So my result here, negative 1/2. Number 96. Let me work this one down the board. I've been working mostly across today, but let me work this one down the board. Again, this negative out front is floating. He'll simply pop into the next step. The negative inside cannot see that negative outside. And so we have to first take this cube root and then see what happens. See if our floating negative is going to participate in anything. Well, the cube root of a negative is negative. And the cube root of 64 is 4. Note the parentheses. They keep those two negatives from bumping into each other. In other words, I want the opposite, right here, the opposite of this cube root, so I want the opposite of this result. So I put that result in parentheses. Now I just have my double negative rule. Negative negative 4, or what? The opposite of negative 4 is positive 4. Not because these two negatives can see each other initially, but because our floating negative finally gets together with the result of this cube root, which also happens to be negative. And those two negatives give me my positive answer. And let's try number 102. The cube root of 0.125. I want something times itself 3 times. That gives me 125 and 3 decimal places. Well, if I'm multiplying something times itself 3 times, and I want 3 decimal places at the end, then the thing I'm multiplying must have 1 decimal place. And the cube root of 125 is 5. So this is a 5 with 1 decimal place. And if we check that, 0.5 times 0.5 times 0.5, well, 5 times 5 times 5 is 125. And there are 1, 2, 3 decimal places in the problem, so we give 1, 2, 3 decimal places to my answer. So yeah, that works. All right. This last bit here in the homework set is very conceptual. Let's start with number 112. It says, simplify each root. Well, here again we have a square and a square root, and they're going to undo each other. My result here is simply going to be 19. Let's deal with this with smaller numbers to get started, okay? Let's consider the square root of 5 squared. The square root of 5 squared, well, 5 squared, if we follow the order of operations, the radical sign is a grouping symbol. You simplify inside it before taking that square root. 5 squared is 25, and the square root of 25 is 5. The square root of 11 squared. 11 squared is 121, and the square root of 121 back to 11. However, watch this. The square root of -5 squared. If I simply follow the order of operations, if I square this -5, I get positive 25. You square -5, you get positive 25. And now the square root of that 25 is positive 5. So my question to you is this. What is the square root of x squared? Well, at first it looked like it would just simply be x itself, right? My 5 here, my 11 there. But what if x itself represents a negative number? Then squaring is going to clear that negative off. And my result will still be this positive answer. It'll be the positive 5. In other words, here it's just the 5. Here it's just the 11. Here it's just the 5. The -5 with its negative stripped off, because squaring strips off that negative in that middle step. Now, can you think of any other thing in algebra that will strip off a negative for me? Absolute value. Without knowing actually what x represents, whether it's a positive number, a negative number, or 0, I cannot tell you whether the answer will be x or the opposite of that base, x. Here it's the base itself. Here it is the base itself. Here it is the opposite of that base. But I can tell you it will be the absolute value of that base. Every time. Absolute value of 5 is 5. Absolute value of 11 is 11. Absolute value of -5 is positive 5. So this I can tell you every time. Look at the brown box here on page 656. The first brown box says the square root of a squared for any real number a. So I don't know if a is positive, if a is negative, if a is 0, but I do know that the square root of a squared will be absolute value of a. What about when it comes to cube roots? Well, the cube root of 5 cubed. The cube root of 5 cubed. 5 cubed is 125, and the cube root of 125 is 5. What if that base in that radicand were negative? Cube root of -7 cubed. Well, an odd power doesn't strip off a negative. -7 quantity cubed is -343. It keeps its sign. And that's not a problem with an odd index. We can take an odd index of a negative radicand. The answer here will be -7. So if I ask you, what is the cube root of x cubed, every time the sign will be preserved. The sign does not get stripped off. So the result will be x itself. So if we generalize this, a moment ago we had what? Square root, which you don't write that index, do you? Square root of x squared had to be absolute value of x. Because whatever the sign is of whatever x represents is going to get stripped off by that even power. But when it's an odd power and an odd index, nothing happens to that sign. The sign remains intact. So it is just x itself. And what we discover is that what works for squares works for all even powers and indices. What works for the cubes works for all the odd powers and indices. In other words, if I were taking the fourth root of x to the fourth, that's an even power, it would end up stripping off any sign that x may have had if x represents some negative number. And so this will be the absolute value of x. However, if this were a fifth root of x to the fifth, an odd power does not strip off a negative. And so the answer is just going to be simply x. Our second brown box on page 656. It says if n is even, then the nth root of a to the n is absolute value of a. Okay, that's our square here. That's our fourth here. It goes on to say that if n is odd, then the nth root of a to the n is simply a. That's our cube here and our fifth right there. Because odd powers and odd indices do not remove or choke on a negative. Okay, so with that in mind, let's go back to number 112. And if we use the brown box that we just looked at, what she's wanting us to practice is this. The square root of something squared is the absolute value of that something. In this case, it's just simply 19. I'm not too worried about this intermediate step since 19 is just a positive number. 19 is just a positive number. Well, then the square and the square root cancel. Boom. But she's wanting us to practice this idea of when my power and index are even, I need absolute value bars, especially when variables are involved. Let's keep going. Number 114. The square root of negative 13 squared. Now, if I wanted to, I could crank this out using the order of operations. 13 is not a bad number to work with. You square the negative 13, you get positive 169. Take the square root of 169, you get positive 13. But she's wanting us to look at it in the light of this brown box, the second brown box on page 656. That the square root of a square is the absolute value of that base. And the absolute value of negative 13 is 13, which of course we got by the order of operations as well. Let's continue, and let's use each time now the idea of that brown box. Number 116, the sixth root of negative 4 to the sixth. That's an even power, even index, so we're going to get the result as the absolute value of that base. And the absolute value of negative 4 is positive 4. And of course that happens again because that sixth power is going to strip that negative off. If I were to work this by the order of operations, those numbers are starting to get a little big, so I really don't want to crank that out. I'm beginning to appreciate this brown box as the numbers get bigger and bigger. Number 118. Number 118, the fifth root of negative 8 to the 5th power. This is an odd power, an odd index, so it does not involve the absolute value bars. Negatives don't get stripped off by odd powers. So my result here is simply the base itself. Notice these were all even, and so we use the absolute value. This last one was odd, so it's just the base itself. Number 122. Again, the instructions say simplify each root. In some problems in future sections, it will say assume variables represent positive real numbers. And in those problems, we don't have to think about these absolute values. But no conditions were given here on x. X could be any real number. It could be positive, it could be negative, it could be 0. So what's the best I can say about this? Well, first, that negative is floating. Let me work this one down the board. First, that negative is floating. So he just jumps into the next step. And what do we know about the square root of x squared? Well, the power and the index being even mean that it will involve an absolute value. The square root of x squared is the absolute value of x. And without knowing anything else about x, that's as far as we can go. Number 130. 130 is going to take a little extra step as we think about this. We're also going to learn some rules in future sections that will cast a different light on this type of problem. But for now, we want this to be the 4th root of some 4th power. Can I write this as the 4th root of something to the 4th? K to the 20 is what to the 4th? It's K to the 5th to the 4th. Power to a power, you multiply the exponents. And so K to the 5th to the 4th is K to the 20th. And so now I have the 4th root of something to the 4th. And the 4th root of something to the 4th is the absolute value of that something, because the 4's are even. So my absolute value is involved. This will be the absolute value of K to the 5th. Without knowing anything else about what K represents, that's all I can do. Now, there is a little glitch in this type of problem. I don't see that it appears in the homework, but let me just go ahead and show you this. The 4th root of whatever, W to the 24th. If I work it the same way, that's going to be the 4th root of W to the 6th to the 4th. The 4th root of a 4th power is just that base in absolute value bars, because those 4's are even. So this would be the absolute value of W to the 6th. But that's not simplified this time, because 6 is even. W to the 6th. I don't care what you plug in for W. W to the 6th is going to be some non-negative number. If W is negative and you raise it to an even power, it's going to turn out positive anyway. W to the 6th must already be a non-negative number, and the absolute value of a non-negative number is just the number itself. This is something we'll get a little more excited about in college algebra, algebra with apps. But strictly speaking, This step right here is not simplified because I know that w to an even power is non-negative, and the absolute value of a non-negative is just that argument itself. So that's our look at section 10.1. I'll let you get to that homework.